Hello everyone, this is Vahe, and I'm going to be going over experiment 5x, which deals with using LT-Spice to do AC analysis of circuits. So these are circuits that have sinusoidal sources in them, and in particular we're going to do 3 different circuits. Here's this first circuit that you're seeing on the right. Okay, and there's 2 more circuits that we'll be seeing. So we'll see a circuit with a capacitor like this, okay, and a circuit with an inductor. Okay, what's common about these circuits is that the voltage source is all the same. In all cases, the voltage is a 10-volt sine wave source, so the voltage goes from 10 to minus 10, and the frequency omega is 2 pi f. And that f is the frequency, right? And the frequency is going to be 1 kilohertz or 1000 hertz, which means 1000 cycles per second. And the period, the duration of one cycle, is 1 over f, or just 1 millisecond. Okay? In each of these cases, we're going to be running the simulation for 5 milliseconds. Okay? And so much of the information here is going to be given to you. So the circuit that I'm going to give you, the sample circuit, will have the voltage source and the simulation command already in there. And it'll be a way for you to start, and then you enter the rest of the component values, and then you can go on from there. Okay? So let's just get started, because the simulation is going to be done on LT-Spice. So let's just jump right into LT-Spice and see how we can, simulate these things. And I'm also going to give you some of the tips and tricks, etc., that's involved in doing some of these calculations. But overall, if you know LT-Spice, obviously a lot of the stuff is going to be maybe a repeat of what you already know. Okay, so let's just open up LT-Spice here, and so this is what I'm going to give you. Okay, this is your starting point. So this is a B source, behavioral source, and you see already I've entered in 10 sine 2 pi 1000 1k, right, times time. In LT-Spice, if you want time, you put time. It doesn't understand t. And the transient command, this will run a time analysis, right? So we'll not just give you values like we've seen before, it'll actually give you waveforms in time. So it's called transient analysis, and the command has already been entered in 5 milliseconds. Okay, so actually, you don't really have to enter in anything but just the components and their values, to get started. So let's just go and look at the first circuit and go from there. So the first circuit is just resistive, and let's just get those values, right? So get a resistor here and rotate, and maybe place it right here. And the second resistor, of course, we're going to rotate those as well. So let's say rotate, or however you do it, doesn't really matter how you do it. So here are the 2 resistors, and in the simulation the first resistor was 3.3 kilo ohms, so it just entered 3.3k. So as you know, LT-Spice understands these, when you say K, it understands it's kilo ohms, right? So you don't have to put 3.3, you don't have to put 3,300, right? So it's going to be 6.8K. All right. So that's entered in. And I just wire it up, right? Here's the wiring. Okay, very straightforward. Go through, and then come back here to ground, and you got it. That's it. This is the first circuit. Very straightforward. But like I said, I'm not going to give you the whole circuit this time. I expect you to be able to do some of these things now, because you're more experienced in it. That's what I assume. Okay. Okay, so now we're pretty much ready to simulate the circuit. There's some other things obviously we can do. For example, we can number the nodes. The bottom node is already numbered as node 0. We don't really have to number that, but other nodes, we can go to the node, and when the cursor turns to a cross, right click, label net, and you can put anything down here. Let's say you put 1 for node number 1. Okay, you put that there. Oops. Looks like it didn't take it. Let's try again. Put in 1, and here it is. And then right click to get out of that mode, and then do the same thing over here. Right click, label net, and then you put in 2, okay, and then you put that wherever you like right here. And then it kind of has a copy of it moving around, but you probably don't want to put that anywhere else, so you right click to get out of that node. So now we have node 1, node 2. We saved this, and we're ready to simulate. The simulation command is on the bottom already, .tran 5 milliseconds. That will simulate this for 5 milliseconds, so everything is ready to go. As I said in the write-up, you're going to see in the write-up that all you got to do is enter the resistors, label the nodes, 1, 2, you're ready to go, okay? And then click the running man, okay? And a lot of other circuits are showing up here because I have a lot of things open, but this is the one that I have right now, okay? And let's take a look at this one. So now we can plot pretty much everything. Like, for example, if you want to plot the input voltage, you can notice that when you bring your cursor near a node, it turns to this red probe. And if I click on that, it'll plot V1, right? V1, which is the same as the voltage of that source, because that source is between node 1 and ground, right? So it's V1 minus 0, right? So if I click on that, there's the source. It's a 10 volt sine wave as expected, and as you look at it, it's got a period of 1 millisecond, and it's gone through 5 milliseconds because we simulated for 5 milliseconds, or 5 cycles, 5 periods. Okay, what else can we plot? Well, I can plot the voltage V2, right? Here you have to go back and forth between the diagram to make sure you're plotting the right thing. Like, see, if you look over here, VR2 is node voltage at 2 minus ground, right? So if I go here and plot V2, right, then I get voltage 2 right there. Okay, plots it right on the same graph. Okay, well, what else can we do with this? Well, you might not want to have all the waveforms on one graph. So you can have separate panes, right? P-A-N-E, okay? So if I go to the graph, okay, notice that we have the schematic window, and we have also the graphing window. And by clicking on the window top there, you can make the different things active. So now the graph window is active. Okay, what can we do with this? Well, if you right click in the graph window, and you can say add plot pane, okay? Click on that, and now a new pane opens up where you can put new graphs, right? So as you click on the top or the bottom, you see that the graph area is being highlighted, right? So if you want to put one of the waveforms up on top, it's very simple. Let's say I want to put V1, the input, on the top pane. What you can do is take your cursor, go on the label V1. You see that cursor turn to a little index finger now? Left click on it and drag, and there you go. Okay, so you can open as many panes as you like, and if you don't want them, you can delete them as well, right? So I can right click and say add plot pane, and maybe I don't want it, right click on it, delete this pane, so you can add and delete panes and move things in and out of them as you like by just going to the label, right? Turns into a little index finger, left click, hold the click down, hold your left mouse button down, and drag. Okay. All right. So this is how you measure the voltages. But there's another voltage, right? There's another voltage that I didn't mention. And if you look over here, right? How about VR1, right? VR1 is between node 1 and node 2. Instead, it's V1 minus V2, right? So how do we measure that? How do we measure that in the simulation? Okay. I'm going to show you the trick now. Watch carefully. So let's say I want to do V1 minus V2, right? So if I take my cursor, bring it to 1, notice it turns red, right? If I want to 2, it turns red too. But I don't want V1 or V2. I want V1 minus V2. Here's how you can do it. bring your cursor to the plus terminal that you want to measure, right? Because VR1 is being measured left to right. So you go on the left node, you see the probe is red, correct? Now, click the left mouse button and keep it down, hold it down, and notice that now the probe turns to black. Now move your cursor, you see what's happening? It's like a empty cursor with no color on it until you go to that next node. It turned black, right? So now you have the red on the left, black on the right, plus minus left to right. Now let go your left mouse button. There you go. And you see what it plotted? V1 comma 2. That means V1 minus V2 in SPICE notation. So that's V1 minus V2. So now you want that in a different pane? Sure. Right click, add plot pane. Maybe we want V1 on top. Maybe we want R1, which is V1 comma 2 next, and then there you go. Now you have this whole pane, and this is the way you should have it, right? If you want, because I'm going to ask for a certain order of these things, and it's quite simple. Then how do you capture this? Well, you just do what? I mean, you know how to do this by now, right? You just go and say Tools, copy bitmap to clipboard, paste. Same thing, same old deal. So you can actually definitely paste waveforms, right? You can paste waveforms pretty easily. Just go and just like pasting, how you copy and paste the schematic, you can copy and paste the waveforms the same way. You just have to make sure that that window is highlighted. Right? So right now I'm highlighting the schematic window. If I say Tools, copy bitmap, it'll copy the bitmap of the schematic. If I want the bitmap of the board, right, or the waveform, then I go make that active. Correct? So it's as simple as that. Now, what else can we do? Well, we can measure the currents, right? How do we measure the currents? Well, that's pretty easy too. Go to the schematic, right? And then let me just clear all these for now. Let's delete all these traces. So it's as if we're starting from a clean sheet, right? So I can just delete this. Right click and delete this trace. You can start from scratch, or you can rerun the simulation if you like. Just click here and just say run, and it'll rerun the simulation. And here we are. Okay, so let's measure IR2, for example, right? So if you remember IR2, right? If you look here, where's IR2? Well, it's top to bottom, right? Okay, let's take a look. Okay, so what you do is you take your cursor again, right? You go on top of the resistor, and you see there's an ammeter, there's a current meter, but it's pointing up. We want the current going down, not up. Okay. How about this resistor? Oh, look, it's going the other way too. It's pointing to the left. I want it to point to the right. So if you clicked on this, you could measure the current that way. But if you see the current meter pointing the other way, very simple fix here. All you gotta do is just rotate the resistor. I mean, it's not really rotating it's not gonna change the result. It's gonna make it easier for you to plot the current waveform. So go to where it says move, okay, and then take this resistor, okay, and then do Control R, pop it back on. Same thing with this resistor here. Take it, Control R, okay, and now rerun the simulation. Okay, nothing really changed. But now if you go on here, you see the current direction, the arrow, left to right as we want it. How about here? Okay, let me just zoom out so you can see everything. See, you go over here, you see the current, top to bottom. So just click here and click here, you got it. In fact, it's the same current, right? Obviously. So, but we can order it. Add plot pane, IR1 on top, IR2 on the bottom. You're in business. So order of the waveforms is actually pretty easy to do. It's just using plotting the, it's basically adding and subtracting and deleting panes, and then using the mouse button and just dragging things up by the label. You hold it by the label, where it's just IR2, IR1. Those are the labels, right? And you can see everything plotted really beautifully, right? Okay, so all we're doing is just remember that if you see, I mean, you have to remember that in this simulation, you want the currents to be measured in a certain direction. So if you're not seeing that, just like I say, just go ahead up here, use the move command. It's this open hand here, right? And go on the resistor and take it out and then rotate it twice, 180 degrees, put it back on, and it'll give you the right current meter direction. You're just changing the current meter direction, that's all. Okay. Okay, what else can we do with this? Well, we can measure the power dissipation, right? For example, let's say we want the power dissipation, or let's say power absorbed, right? It's the same thing for a resistor. Let's say I want the power absorbed for R1. What do? Well, we know what to do if it was a constant voltage, right? We just do, if we look at our diagram here of the measurement, right? Let's look at VR1 and VR2, and let's look at the currents as well, right here. Right, so if I wanted the power dissipation in resistor R1, I could do VR1 squared over R1, right? I can do R1 times IR1 squared, right? Or I could do IR1 times VR1. Either of those three would be okay. Similar for R2, right? And when these are constants, we just calculate them as constant numbers. But now, remember, IR1 and VR1 are not constants, right? They're not constants. They're actually functions of time. So what do we do with that? Well, we can still multiply VR1 times IR1. Let's take a look at that and how we do that. Okay, so let's start with a clean sheet of paper here, as so to speak. Okay, so let's just delete this trace. How do you delete it? Go here, right? Cursor turns to an index hand, index finger, right click, delete this pane, all empty, right? So let's say for R1, right? We want IR1. Here's IR1, okay? And then VR1 is like this, right? You go here, left click, leave it on, go on the right side, and let go. Okay, that's V1 comma 2, right? So if I do right click here and say add plot pane, come over here. Okay, so I have the voltage across the resistor on the top, current through the resistor on the bottom. I don't multiply these, right? How do I multiply these? There are two ways. There are two ways to multiply these. One of the ways is like this. So I can say, okay, I want to plot this new function v times I. I right click and let's say I add a plot pane. Okay, so I want to put it up here. So it turns out that with LTSpice, when I have the waveforms, I can do math with these waveforms, right? With these voltages and currents. So I want to show you that. So I'm on the top pane here, right click, okay, and then I can say, let me add a trace. In other words, add a waveform, that's what that means. Click on that, now I have a list of voltages and currents that I can deal with, okay? So what do I want to do? Well, I want to do V1 too, right? So V1 minus V2. It doesn't show up here, but I can simply write it down because I know from the blue waveform, if I do V1 comma 2, that's my V1 minus V2, that's my VR1, right? And I can multiply it by IR1, right? Well, IR1 is here, so I can just pick that out. And there we go. And I say, okay, and there it plots. You can see it's in milliwatts. LTSpice knows I'm multiplying voltage times current, so the units are watts. There you go. That's the power dissipation, right, as a function of time. It goes from 0 to almost 3.3 milliwatts, and it oscillates. It oscillates at twice the frequency because you're doing basically like sine squared, right? When you do sine squared, you get actually twice the frequency. But notice that it's never negative. It's always positive, right? Because resistor always dissipates or absorbs power and then gives it off as heat. It's clear from here, right? It's clear from here. And looking at that, we can also have an idea about what the average is, right? It seems to be oscillating between 0 and 3.3. So what's the average? Right in the middle, about 1.8 milliwatts maybe, something like 1.85, something like that maybe. It seems to be doing that. We don't know for sure. Also the energy, how much energy is absorbed, right? So these are more questions, but certainly once we have the power waveform there, we can ask these questions. Now, there's another way to get the power, and this is the easy way. Watch this, okay? So I take my cursor now, and I'm inside the inside the schematic, right? So let's say I want to measure the power dissipation R1. So I take my cursor and I go right on top of the resistor, okay? And when I do that, the current meter shows up, right? But I'm not interested in the current. What I do is I click the Alt key. You see, I'm clicking the Alt key and unclicking it right there. You see it's turning into a thermometer? Okay, isn't that interesting? So what you do is you hold the Alt key down and it turns into a thermometer. Left click. When you do that, you're going to get the power dissipation. And in fact, it's plotting the same thing that I have, so it's not changing anything. So let me start from a clean sheet of paper so you see that it's going to do that for me automatically. I don't have to do what I just did with the waveforms. I just showed you that to show you you can actually multiply any waveforms that you want. Any way that you like, actually. So let me get rid of this. Clean sheet of paper, right? So I'm over here. I go on R1, click Alt. There you go. That's the power dissipation in R1. You can see V12 minus IR1. It did it automatically. How about for this resistor? Well, it's going to do V2 minus 0, or just V2, right? Times IR2, right? Watch. I go right on it. There's a current, right? You see the current is pointing up. Maybe I want to change that. Yeah, I can change that too if you want. Like, for example, I can go here. I can go to the move, right? I can take that out and I can do Control R, just to make sure I have the right direction for the current, right? Like that. Rerun the simulation. Nothing's going to change on this waveform, right? If I go on it, you see the current is pointing down now. Okay, if I hit Alt, thermometer, click, that's my power dissipation in resistor R2, right? So if I add a plot pane, you can see that the top is PR1, the bottom is PR2, right? Now, how do we calculate this average power and the energy absorbed, right? So here's another trick, okay? So you can do this by looking at the waveform and try to integrate and do all that kind of stuff, but I have a shortcut for you, okay? And if you watch the video here, you get these little tidbits, right? So if you take the cursor, I have the cursor now, I go on the where it says V12 IR1, this is the power dissipation in R1, or power absorbed in R1, right? So if I click the control button and click on the waveform name, the waveform label, I get this window and it tells me the average is 1.61 milliwatts. Okay, 1.61 milliwatts. And then the energy is 8.08 microjoules. That's the integral, actually. It says integral, but integral of the power is the energy, actually. So that's what that is. It's very easy, right? So you want to know the average power and the energy, right? Average power absorbed or energy and energy absorbed together for you. Go on the label of the waveform, the power waveform, click the control key, hold it down, click the label, and you get it right away. And you just write those down. It's as simple as that. And it works for anything, right? It even works for a voltage, obviously, right? You can get the average value of the voltage. You won't get energy out of a voltage, obviously, but you do get the average value of the waveform computed this way. So I wanted to show you those tricks as well. I mean, they're not really tricks. These are documented. If you look at the help file, I mean, if you look at the help file from here, help topics, you'll find all these things. I mean, it's not really a trick. So as a summary, what I just told you is that I'm going to give you the voltage source to begin with and the simulation command. You put together the circuits, okay, and then you enter in the component values, as you know, label the nodes, okay, then you run the simulation. And when you run the simulation, voltages can be measured directly, and the difference of the voltages, like V1 minus V2, can be done with that dragging trick. Currents should be measured in the way that the document wants it. If the current meter is in the other way, just move the resistor, rotate it 180 degrees. You should be ready to go there. Besides that, what else? Well, the going to the resistors or any component for that matter, and clicking on the Alt key first, and then clicking gives you the power dissipation. And then once the power dissipation is plotted, going to the label and clicking the Control key and clicking the label gives you the average value of the power absorbed and also the energy absorbed. Okay, and I've gone through all of them, but I'm not going to give these to you. Obviously, I want you to do these because the circuits are so simple, right? Here's the circuit that I just showed, but there's also this circuit with the capacitor, right? And there's this circuit with the inductor. I mean, they're pretty easy to enter. The capacitor, by the way, just enter an 0.1 UF, and LT Spice will change the U to a micro for you automatically. There's nothing for you to do. And then that one is 100 M henries, like millihenries, or 0.1 henries. It's the same thing. And these run exactly the same way. For example, if you go to this circuit here, click the Running Man. I mean, all you got to do is enter one element here, right? I mean, what's the difference between this and the first circuit? Here's the first circuit, right? That we entered. Where is it? Sorry, I can't find my circuit now. Let me find it. Sorry, let me go and find my circuit. It disappeared. Oh, there it is. Right. What's the difference between this circuit and the capacitor circuit? R2 is replaced by the capacitor. What's the difference between this circuit and the inductor circuit? Right. This one. Well, R1 has been replaced by inductor. So if you start from the first one, just one replacement. One replacement. It's pretty easy. Okay? And the simulations run the same way. You come here and you click the Running Man, and then look at the current, right? For example, look at the capacitor current. Oh, it's going down. Okay, that's what I want. There it is. It's the capacitor current. How about this resistor? Oh, look, the current is facing the other way. What do I do? Well, go grab this, right? And then Control R to rotate. Put it back, rerun the simulation. You ran so fast anyway. Go on top of it again. There you go. That's your IR1. There it is. Okay, in fact, they're the same currents, right? Add plot pane, and here's IR1, and here's IC1, right? That's pretty much it. And the other ones are pretty much the same. Go through and do it. So I try to keep the video to less than half an hour, and we're about 28 minutes right now. So anyway, I'm gonna stop here, and if you have any comments, please put it on Piazza. But I think most of you are doing pretty well and starting early. That's the key for this. Start early, and please use your lab hours. You have a dedicated 3 hours of lab every week. Use those hours to get started on this thing, and it doesn't take much. A lab report is there, copy and paste. I mean, this will not take, like 5 hours, 10 hours, or anything like that. You will be able to finish this, especially if you watch this video, because I tell you all the tricks, which are not really tricks, but they're shortcuts of doing things. Okay? So thanks very much for your attention. I appreciate it. And until next time, take care, and as always, stay safe.